to it. So we've got our origin, O-Y-E-X-E-R-S-A. The origin we can see, a little different. The origin here is there. So when we look at the coordinate plane, we are looking at something that's situated like this. All right, that's good for us to know. The y-axis is velocity. Y-axis is velocity. And we see the units are meters per second, normal units. It goes by ones. The x-axis is time, and it goes by fives and has normal units of seconds. The things we can read are the axes, or v and t, so if there's any question about velocity or time, we're going to read the answer off. The slope, delta y over delta x, the y-axis is velocity, so delta v over delta t, that's the definition of acceleration, the rate of change of velocity. So the slope is acceleration. In the area, we multiply the axes. So v times t, that's units of meters per second times seconds, meters. So the area is the displacement. We notice that we have a velocity, just reading off the values, that starts at a little over 1, decreases to 0, hovers around 0, and then the velocity, the speed increases in the negative direction from 0, and this is kind of important for us to analyze here. This is at rest. And then we might see that this part is slowing down. And then over this segment, we see it speeding up again. And here we have constant velocity in the negative direction. And we said slowing down, speeding up in the negative direction. So those are just things to note reading the graph. And sometimes it can be hard when we're given these data points because the truth is real measurements have a little bit of uncertainty to them. So they may not be a perfect line. So we have to see the forest for the trees here, that what they are looking at is approximately a straight line decreasing, approximately 0, approximately decreasing again, and then remaining a constant -2. So an engineer measures the velocity of a remote-controlled cart on a straight track at regular time intervals. So we got a cart going like this on a straight track, positive direction, negative direction. Showed in the graph above. Which the following did the cart return to its position? So let's analyze the motion here. We start out with a positive velocity, and we see it slows down, so we would expect the dots to get closer together. And at this particular time, it stops. Then it reverses direction, and it speeds up and heads in the other direction. So there's going to be some time when it gets back to this same point. Now, they want to know about the position. And position is related to displacement, which is the area. So if we take the area of this triangle, it's going to be positive, because we have 1/2 base times height, and the base is positive, and the height is positive. So we'll have a positive area. When we look at this area, that's going to be 1/2 base times height. And the base is positive. This is the base. But the height is negative, so we're going to have a negative area. So we have positive area coming out here and negative area coming out here. So what we are looking for is to find that place about right there where this area equals this area. They'll add up to 0. And so we could see then that I drew this in the midpoint. So this is like 7 and, so this is like 7.5. And so clearly to get to that point, it's going to be sometime after, around the 7-ish seconds. So 3 to 5 seconds is here. No, that's when it stops. 5 to 7 seconds. No, it's building up so it gets to that point. 7 to 10 seconds. We think that's the answer. And we look at 10. We see 10 to 12 seconds. That's over here. Definitely not. So our best answer is choice 7. Now, the most important thing to remember about doing multiple choice questions is never to look for the correct answer. Always look to eliminate the wrong answers. But that's why that's the answer there.